Today's video covers separable partial differential equations. So in this last unit, the first half of the unit was Fourier series. The second half of this unit is going to be separable partial differential equations, specifically of two main applications, which are called the heat and wave equations. So if you remember from the very beginning of this course, I said we were going to focus on ordinary differential equations, and that's what we've done up until this point. At this point, we are looking at partial differential equations. So it's exactly what it sounds like, a differential equation that has partial derivatives in it. So in this first video, we're going to look at the background, some definitions, some classifying, and we'll look at how to solve these in general using separation of variables. So let's jump in with a definition. We are going to focus on linear second-order partial differential equations. So this is the general form. If you notice, all of the derivatives are partials. You're going to notice they're all to the first power, which makes it linear. And then second order, because a second derivative is the highest derivative that we have. And in this notation, a, b, c, all the way to g, these are functions of x and y. Now, if g is equal to 0, so if our equation is set equal to 0, we call the equation homogeneous. So if we look at this first example, this example is a linear second order partial differential equation, and it can sometimes be written as PDE. Because the equation is set equal to 0, this equation is also homogeneous. Now, we also classify partial differential equations as hyperbolic, parabolic, or elliptic. So if we calculate b squared minus 4ac for all of the equations, or if we calculate b squared minus 4ac for any linear second-order partial differential equation, the equation is called hyperbolic if that b squared minus 4ac is greater than 0. It's called parabolic if we're equal to 0, and elliptic if less than 0. So if we look at this example number 2, we need to put it into the form that we saw above. So I guess I should let us still see that. So if we rewrite this, this is really 3, the second derivative of u with respect to x, subtract the derivative of u with respect to y is equal to 0. So then using that equation above, that 3 is our a. This -1, looking at our equation, is e. So if we calculate b squared minus 4ac, we have 0 squared, subtract 4 times a times 0, so we get 0. So hence, this equation is parabolic. So now that we've taken a look at classifying, we're going to move on to what is the biggest part of this video, which is going to be solving the solution of a partial differential equation. So starting with a definition, a solution of a linear partial differential equation is a function, u of xy, that possesses all partial derivatives in that linear partial differential equation and satisfies the equation. We are going to find particular solutions by separation of variables. So the idea is that we want a solution of the form u of xy, which is some function of x and some function of y. Then the partial of u with respect to x would be big X of little x times big Y of little y, which I'm just going to write as x prime times y. The second partial of u with respect to y then, for example, would be big X of x, y double prime of y, which can also be written as x, y prime, so on and so forth. Those are just two examples. So that's the idea. This is how we're going to look for a solution. And the way we're going to go about this is just by doing an example. So let's turn the page to the first example. So here we go. We want to find the product solutions of this equation. So we are going to let u of xy, that's our solution, that's what we're trying to find. We're going to assume that we can find a solution of the form, the product of a function of x and a function of y. Then I can rewrite this differential equation as the second partial with respect to x is going to be x double prime y. and that'll be equal to 4. The partial of u with respect to y is just x, y prime. Now, one thing that I want us to remember is that these are all functions of x and y. So when I say x double prime, that's a function of x. So we need to recall that. Okay, so now we're going to rewrite this, switch some things around, and we can notice that we can get x on one side together, and we can get y on one side together. Now, something to notice about this equation is on the left side, this left side is independent of y. This right side is independent of x. Okay, so what this shows us is if both sides are independent of x and y, what does that lead us to? Well, what that leads us to is that they must be constant. So again, if the left side of the equation is independent of y, the right side of the equation is independent of x, the only way that that's going to happen is if those two sides are constant. Okay, so where does that take us? We're going to rewrite that equation, x double prime over 4x is equal to y prime over y, keeping in mind that those are functions. If they're constant, we're going to set them equal to a constant. And we're going to use negative lambda. You'll see why in a minute. So you'll see why we use a negative, but this is called the separation constant. And I'm just going to put, we could use positive lambda also. Okay, so this is going to give us then two different equations. The first equation we get x double prime over 4x is equal to negative lambda, and we also get y prime over y is equal to negative lambda. Okay, so on this equation on the left, if I get everything set equal to 0, I'm going to have x double prime add 4 lambda times x is equal to 0, and then I'm going to have lambda, or y prime rather, add lambda times y is equal to 0. Now, these are the ones that we need to solve. Now, of course, there's three cases that we have to consider. That lambda could be equal to 0, that lambda could be less than 0, and that lambda could be greater than 0. So that's what where we're gonna go to next is considering each of those cases separately. Starting with case 1, where lambda is equal to 0. Those two equations then become x double prime equals 0 and y prime is equal to 0. Okay, so writing this in a more familiar term, this is the second derivative of x with respect to x is equal to 0. So if I differentiate, I'm going to get d big X over d little x is equal to c1. And then if I think I said differentiate before, I meant integrate, so hopefully you knew what I meant. If I integrate again, I'm going to get big X is equal to c1 little x add c2. Similar idea with that y. This is d big Y over d little y is equal to 0. If I integrate, I get big Y is equal to c3. So together, our u then, which was big X times big Y, would be c1x add c2 multiplied by c3. So our u then would be some constant multiplied by x, add another constant. So that would be the solution if case 1 were true. Okay, so now let's look at case 2, where lambda is less than 0. If lambda is less than 0, you're going to see why I'm going to choose to do this in a minute, but I'm going to choose lambda to be equal to negative some constant squared. So then if I go back again to these two equations, I'm going to get x double prime subtract 4 alpha squared times x is equal to 0, and I'm going to get y prime subtract lambda squared times alpha squared rather times y is equal to 0. Now we have to remember how to solve these. If we look at this equation with x, we're going to have to go back to the characteristic equation. So that's m squared subtract 4 alpha squared is equal to 0. So our m is equal to plus or minus 2 alpha. Similar idea on the equation with y, so we get m subtract alpha squared is equal to 0. So our m is equal to alpha squared. Okay, so then our x equation, if we remember, we got all the way up to c3. So this is going to be c4e to the negative 2 alpha x, add c5e to the 2 alpha x. And our y will be c6e to the alpha squared of y. So then, if we go to our solution u, which again is big X times big Y, that's going to be c4e to the negative 2 alpha x, add c5e to the 2 alpha x, being multiplied by c6e to the alpha squared y. So simplifying that a little bit, our u ends up being, when we multiply these two, we're just going to have a constant, which I'm going to call a2, e to the negative 2 alpha x, add alpha squared y. Then we have another constant, e to the 2 alpha x, add alpha squared y. Okay, so both of these, what I have boxed in blue is one solution. What I have boxed in green is another solution. One thing that I want to note to us, particularly for those of us who maybe use the book or look at WebAssign or have been taught something else by a different teacher, is we can use different functions here. And by here, I mean these two. So our solution for x is c4e to the negative 2 alpha x, add c5e to the 2 alpha x. If you use the book, though, or maybe have been taught this differently, instead of using e, you could use hyperbolic cosine of 2 alpha x and hyperbolic sine of 2 alpha x. So if you ever see that, just know that this hyperbolic cosine is just the e. Hyperbolic sine, again, is just the e. Okay, so that was the first two cases. And of course, we have one more case still, which is the case where lambda is greater than 0. I'm going to have a new page, and I'm just going to recall for us case 3 is where lambda is greater than 0. And we're going back to the equation of x double prime, add 4 lambda x is equal to 0, and y prime, add lambda times y is equal to 0. So similarly, what we did before, if lambda is greater than 0, to help us in solving, what we're going to do is we are going to let lambda equal alpha squared. So we end up then with x double prime, add 4 alpha squared x is equal to 0, and we have y prime, add alpha squared times y is equal to 0. So finding our roots, first equation, we get plus or minus 2 alpha I. Second equation, we get negative alpha squared. So what that gives us then, our solution x in terms of little x is going to be c7 cosine of 2 alpha x, add c8 sine of 2 alpha x. And our solution big Y of little y is c9e to the negative alpha squared y. So when we multiply those two together, we get our solution u of xy to be a3e to the negative alpha squared y times cosine of 2 alpha x, add b3 e to the negative alpha squared y sine of 2 alpha x. Now again, we have 3 possible solutions. So we still have those 2 solutions that we had above. So our first solution that we found, u of xy, was that a1x add b1. And then the second solution that we found, u of xy, we found to be a2e to the negative 2 alpha x add alpha squared y plus b2e to the 2 alpha x add alpha squared y. So what I'm saying is these are all solutions. They're all solutions based on the value of alpha and lambda. So a few things for us to write down. If you noticed with case, I forgot a 3. With case 3, we used alpha squared. With case 2, we used negative alpha squared. So some of us might be asking, why did we have to do those separately? So a quick note is that we needed to consider cases 2 and 3 separately because the roots could have been real or imaginary. And so our solution looks different depending on if the roots are real or imaginary. Another thing to recall that lambda and alpha are constants. And so because of that, they could be replaced by C. So if you are someone who references the Stewart book, in the Stewart book, you're going to see C instead. You're not going to see alpha and lambda because those are just represent constants. And then the last thing for us to just remember is that you now can verify that the above are all solutions to the linear partial differential equation that we were given. We're not going to do that, but you could if you wanted to. Okay, so that was our first example. We're now going to go on, talk about a principle, and then do another example together. Yes, it's back. I know you've been thinking, when were we going to do superposition? Well, we're going to do it now. If U1, U2, all the way up to UK are solutions of, this is a homogeneous linear partial differential equation, then U is equal to C1U1, add C2U2, all the way up to CKUK is also a solution. Now, unrelated to that, but just a quick note, your equation won't always separate into x prime over something equals y prime over something. So just know that. Instead, you simply need x and y on different sides. Okay, so let's look at this last example. One thing that I want you to notice before we start solving is we have first partials only. And this time our dependent variable is u, but our independent are x and t. So we are going to let our solution, u of xt, we're looking for a solution that's a product of a function of x and then a function of t. So we know from our equation, we're going to need the partial of u with respect to x and the partial of u with respect to t. So remember, I'm just going to keep this as big X, big T, just to make things a little bit easier for myself. So on the left side of the equation, I have that X. And then when I take the first partial with respect to X, I have X prime and T. And on the right side, when I take the first partial with respect to T, I'm going to have X and big T prime. Okay, so then in this case, like we have in this note above, we need our different variables on different sides of the equation. So if I get my x on the left side, I'm going to have little x, x prime over big X. And on the right side, I'm going to have t prime, little t over t. Now, the same idea applies as applied before. If this side is independent of t and this side is independent of x, but they're equal, then the only way for that to happen is for these to be constants. So now if I solve for x, I'm going to get little x, big X prime, add lambda, big X equals 0. And likewise, I get t prime times little t, add lambda times big T equals 0. Now, we don't really need to separate this into 3 cases like we did before. The first case that's going to matter is if lambda equals 0. And if that's the case, we're going to get little x, big X prime is equal to 0. So if I divide out that x, I have x prime is equal to 0. So if I integrate, I'm going to get x is equal to c1, and likewise t would equal c2. So our u then of xt would just be some constant. Now, the other case is if lambda does not equal 0. Now, we don't need to split this into two different cases, and you'll see as I'm going through solving. If lambda does not equal 0, then I have little x, big X prime, add lambda times x is equal to 0. So I'm trying to get the big x's together, so I have little x, big X prime is equal to negative lambda x. So this gives me big X prime over big X is equal to negative lambda over x. So at this point, we need to stop and say, does it matter here if lambda is positive or negative? So if lambda is positive or negative, does that influence my solving in any way? And the answer should be no. In the previous example, the answer was yes, because if the roots could have been complex or real. Here though, it doesn't matter, we're just integrating. So when we integrate, we get natural log of big X is equal to negative lambda natural log of little x plus c4, of course. Now if I apply an e, I'm going to get big X as a function of little x is equal to c5 x to the negative lambda. Likewise then, big T of little t would give us c6 t to the negative lambda. So then if this were the case, our solution u of xt would be c7 xt to the power negative lambda. So both of these you could verify are solutions to our original linear partial differential equation. And a few notes, again in the book you might see that written as c instead of lambda because c is a constant. And then again, just to reiterate why we kept this as one case instead of two, when we get down to here, to integrating, it doesn't matter if this number is positive or negative. We're still going to end up with the same antiderivative. Now, if this were second order, where we would be looking for solutions of a characteristic equation, it would matter if those solutions, because those solutions could be complex or real, but that case does not apply here. So thank you for watching. Moving forward, we're going to be looking at some classical partial differential equations, namely the heat and wave equations. So until next time, thank you for watching.